Hello, welcome to KIG 3013 Heat Transfer in Conduction Lab for Group C1. Our team member is me, Danish, Abinash, Kohanesh, Muhammad Firdaus, and also Muhammad Fakan. Next, for introduction, heat transfer is the movement of thermal energy from a higher temperature system to a lower temperature system. Conduction involves a heat transfer through solid or stationary fluids via direct particle interaction. Next, this experiment focuses on analyzing temperature distribution and determining the thermal conductivity of a material using a brass disc setup.
Hello everyone, my name is Abinash and today I'll be demonstrating our experimental procedure. We begin by setting up the apparatus according to the figure, carefully inspecting all electrical connections between the power supply and the unit to ensure secure contact. Next, we open the water tap to initiate coolant flow. This is critical to maintain heat sink stability and prevent system overheating. Once the flow was steady, we activated the main power supply flow followed by the power source unit. We set the initial output to 10 watts and allowed a 5-minute window for the system to reach thermal stability. Using integrated sensors, we measure temperatures at points T1 through T6. To ensure accuracy, we repeated these measurements twice to calculate an average, then scale the power output to 30 watts and 50 watts, recording all data for analysis. Finally, we reduced the power to 0 and switched off the source. We kept the cooling water circulating for an additional 5 minutes to prevent thermal damage. Once the apparatus cooled sufficiently, we closed the tap, turned off the main wall socket, and safely disconnected the equipment.
I'll be explaining our results using Excel. We started by importing our raw data into the Excel, and then as you can see, as the power increases, the temperatures also rise. But across all tests, the temperature consistently drop as we move from the 4 mm inner radius to the 54 mm outer edge. So as you can see also, the higher power input resulted in higher starting temperatures and steeper gradients. Looking at our first Excel plot, temperature versus radius, you will notice a distinct curve. This non-linear profile is exactly what we expect in radial conduction. Unlike a flat wall, the area here expands as heat moves outward, causing the gradient to shallow out toward the edge. And then for the linearization and calculation, to calculate the thermal conductivity, we use the ln function in Excel to linearize our data. By plotting the difference temperature against the natural log of radius, we achieve a straight line. So I use the add trend line feature to get our slope from the graph, and then we plug this slope into our radial conduction formula, ensuring our 3 mm thickness was converted to meters for an accurate K value. And then finally, our error analysis in Excel show that at a low 10-watt input, the percentage error was high. However, as the power increased, our experimental K value got much closer to the theoretical value for brass. This proved that a larger temperature gradient provides much more reliable data.
From table 7.2, we observe that temperature generally decreases from the inner radius to the outer radius for all power inputs. This matches the expected heat flow from hot to cold region. However, the higher the power inputs, we saw slight local temperature increases. This is likely due to the measurement errors, sensor accuracy, and poor thermal contact between the sensor and the disk surface. Figure 7.5 shows a non-linear temperature profile along the radius. This agrees with theory for radial conduction. Unlike a flat wall, cylindrical conduction gives a logarithmic temperature distribution because the cross-sectional area changes with radius. Figure 7.6 plots temperature difference against the natural log of radius. The graph is approximately linear, which supports the Ford's law of cylindrical system. The slope here relates directly to the heat transfer rate and inversely to the thermal conductivity. At table 7.8, the calculated thermal conductivity values deviate significantly from expected brass values. At low power input of 10 volts, the conductivity is very high, giving a large percentage error. This happens because the small temperature gradient amplifies uncertainties like heat loss, power fluctuation, and sensor sensitivity. As power input increases, the temperature gradient becomes larger. This improves measurement reliability and the percentage error decreases. A larger temperature differences reduce the impact of noise, heat loss, so the calculated conductivity gets closer to the true material property.
Discussion on apparatus design and heat transfer behavior. Okay, first, the apparatus design helps ensure accurate heat conduction. The air gap surrounding the disc act as an insulating layer, reducing the heat loss due to convection. At the same time, the heat-resistant casing minimizes heat loss to the environment. So these features ensure that conduction remains as the dominant mode of heat transfer. Next, the effect of material conductivity is very important. Material with high thermal conductivity, such as brass, allow heat to flow more easily, resulting in a smaller temperature gradient. So in contrast, the material with lower conductivity will show a larger temperature difference. This is why material selection is very important in engineering application like heat exchanger and insulation systems. Okay, discussion on the effect of temperature and experimental improvement. Okay, the thermal conductivity is affected by temperature. So for metals, as the temperature increases, the conductivity slightly decreases due to the increased lattice vibration. This will interfere with heat transfer and also affect the readings. Although our results are precise, they are not fully accurate. One improvement is to apply thermal paste at the sensor contact points to eliminate air gaps and obtain more accurate temperature readings.